non-causality that you can't easily explain with this simple idea that the quantum state is the state of knowledge. And so we talked about how computational speed up, Bell inequality violations, and contextuality are on that list. And the one that you probably have heard the least about is contextuality, and that happens to be the thing that I'd like to spend a lot of time thinking about. So I'm going to tell you about contextuality, and not so much about the other two. So I'm going to start by giving you just sort of a bit of a feeling of what contextuality is, and then I'm going to sort of start over again and do it in a lot more detail, more rigorously. So the Cauchy-Specker theorem, which you might have heard about, is from 1967. This is Ernst Specker. And actually, the ideas of the Cauchy-Specker go back to an earlier paper of his from 1960. So he was actually thinking about this in the late 50s. So I want to tell you about an idea that he described in his first paper on this subject in 1960. And so let me explain it like this. He said, imagine a universe that has the following sorts of operational features. So imagine that there's a system in this universe, and there's different measurements you can do on it. And just like the quantum world, there's certain limits on what you can measure jointly. So in quantum mechanics, we can't measure position momentum simultaneously. We can't measure z spin and x spin simultaneously. So from an operationalist perspective, what does that mean? It means if I think about the statistics of, say, a z spin measurement and those of an x spin measurement, there does not exist a third measurement whose outcome would allow me to, there does not exist a third measurement such that I could process the outcome of that measurement and thereby simulate both the z spin measurement and the x spin measurement. If there was such a third measurement, then I could say, oh, x and z spin really are jointly measurable because I can simulate them both by processing a single measurement. So what Specker asks is, suppose you imagine that there are pairs of measurements, triples of measurements, such that pairs of them can be measured jointly, right? So there's some third measurement, call it maybe M1 and 2, which processed in two different ways simulates M1 and simulates M2. So these guys can be measured jointly. And this pair can be measured jointly, and this pair can be measured jointly. But the three cannot be measured jointly. Okay? So that's the limitation, that you cannot jointly, you can't find another measurement that simulates all three of these guys at the same time. Okay, so imagine that, and then he says, and now imagine also that there's a preparation procedure that you can do, such that whenever you measure, say, M1 and M2 jointly, these are each binary outcome measurements, so I have two little LED lights on each of them. I always find that their outcomes disagree. So if I get the 0 outcome on one, I get the 1 outcome on the other. And if I get the 1 outcome here, I get the 0 outcome there. And that's true for no matter which of these pairs I choose to measure. So suppose that's what's going on. Well, what would be surprising about that kind of universe is that if you tried to imagine that there was some matter of fact about what the outcome of the measurement would be, fixed by the properties of the system that you fed into the measurement device, you'd encounter difficulty. Because suppose you thought that the properties of the system were such that deterministically it would give the green outcome for measurement 1. Well, you know that if you measure M1 together with M2, then it has to give the red outcome for M2 because they have to be anti-correlated. So that says that the properties of that system, the ones that give you this green outcome, have to be ready to always give you this red outcome. But it also means that because if you measured M2 with M3 and you got red here, you'd have to get green here to always get the anti-correlation. So that system has to have properties that fixes this to be green. But now we have a problem, because if I measure M1 and M3 on that same system, this specification says that they should be correlated, not anti-correlated. They should always agree. So if there are some properties that fix deterministically the outcomes of the measurement, they cannot satisfy the correlations that I've described here. You can't find that for every pair of these measurements you get anti-correlation. It's just not possible. So is that idea clear? Because this is the absolute most simple version of contextuality. It doesn't get any more simple than this. But if it's unclear, we should stop and try to clarify it. Is it good? Okay, so I can't have these three disagreements. If I ask, what's the probability? So let's say we're playing a game, the pair of measurements that's going to, so you get to prepare the system. I'm going to do one of these three pairs of measurements. I'm going to choose that pair of measurements at random, probability 30. What's the probability that you can win this game? Well, if you sort of prepare a system that's ready to answer, say, green, red, green, then you'll win if I happen to choose one of these two tests. You'll lose if I choose that test. So your probability of winning is always less than or equal to 2/3. So you could say if the world is a place where the outcomes of measurements are fixed deterministically by the properties of the system, then the probability of success in this kind of game is always bounded above by 2/3. So you can think of that as a non-contextuality inequality. So why do we call this non-contextuality? One way you could try to get around this problem is by saying that the outcome of measurement 1 depends on whether it's being measured together with M2 or M3. So implicit in what I've said so far is I've said, look, I get the green outcome if I measure M1 together with M2, and I also get the green outcome if I measure M1 together with M3. If I relax that assumption, if I say, oh no, the outcome for M1 could be different for M2 and M3, then I can satisfy all these constraints. So when I say that the outcome of M1 doesn't depend on the context, is it measured together with M2 or is it measured together with M3? That's the context of the measurement. So if I say it's independent of context, equivalently I could say it's non-contextual. So any non-contextual and deterministic assignment of values for each of these measurements will give you a probability of success at most 2/3. And so it's like a Bell inequality. A Bell inequality is based on the assumption of locality. This is based on the assumptions of non-contextuality and determinism. Okay. So I've just said this already. If it's deterministic and independent of context, then that's the Bell. So it turns out you can generate other examples of this. Let me give you sort of an idea. For every frustrated network, you can get one of these non-contextuality inequalities. So suppose every node represents a binary variable. Edges, so every node is going to represent actually a measurement you can do. It's a binary outcome measurement. And every edge is going to mean these measurements are jointly implementable. So each of these is 3 measurements that are pairwise jointly measurable. And straight line means the outcomes agree, dashed line means the outcomes disagree. This is the frustrated network we saw. Any assignment of 0s and 1s to these nodes cannot be anti-correlated across all these edges. Just because, as I move around, if I assign 0s and 1s, it's going to have to be that some pair of edges both get assigned 0 or both get assigned 1. But these other patterns are also frustrated networks. So if these guys have to agree and these guys have to agree, then it follows that these two have to agree. So I can't have disagreement here. And similarly with these sorts of guys. So these are all frustrated networks. If you write down 4 nodes, you get some more frustrated networks, like this guy here, where all these agree, but this one disagree. Obviously, there's no set of values that will satisfy that either. And similarly with all of these guys. So if I have 4 binary outcome measurements that are jointly measurable in pairs, and I say that the correlations have agreement and disagreement along these lines, then I find that a non-contextual value assignment won't be able to achieve all of these kinds of correlations. So take this example where we have agreement between all these pairs of measurements and disagreement across here. So that's another frustrated network. And the probability, the probability of success for this kind of task is going to be 3/4. Because I can assign, for example, 0s to all these guys, and then I satisfy all these lengths, but I won't have disagreement here. And if I change things and I say, oh, I'm going to put a 0 here and a 1 here so that I have disagreement here, well, then one of these links is going to have to be a disagreement. So one of these correlations is always going to be wrong. So at best, you can succeed 3/4 of the time. So that's another non-contextuality inequality. Yes?
Do you have relationships between the classes of graphs of frustrated networks and the inequalities that you get?
Yes. So I guess you could say that for every frustrated network, you get a non-trivial non-contextuality inequality. And that means that you could imagine a world which violated that inequality. So I could imagine a world where for every node in my network, there's a measurement associated with it. For every edge, there's a notion of joint measurability for those measurements. And then, this particular pattern of correlations, I could imagine that when I go and I do, say, this pair, I find that the outcomes always agree. when I measure this pair, I find the outcomes always disagree.
My question was more like, given a class of frustrated network graphs, for example, like could we say, for example, it's this type of graph, hence we know that they'll give us this kind of contextuality inequality.
What do you have in mind when you say different kinds of contextuality?
For example, like you could have, depending on how connected the graph is, or things like this, or how many vertices, how many edges, or like you could have some kind of theory where you're given a graph and then you know coming out of that you have an inequality.
Well, there's another kind of graph which is associated with non-contextual inequalities that's been looked at by Cabello and Severini and Winter. So there's a paper on the archive by those three guys. It's not quite these sorts of graphs, but it's a result very similar to what you're saying. So they characterize an experiment by a certain kind of graph, and then they calculate certain graph theoretic properties, which end up corresponding to, for example, the upper bound on what you can achieve non-contextually. Another characteristic of the graph tells you what the upper bound is on what you can achieve quantumly. That's called the Searleson bound. So I think it's the connectivity of the graph gives you this thing, and the Lovash theta number of the graph gives you quantum bound. But it's not the same kind of graph as what I'm plotting here. So to make this look a little bit more familiar, imagine that you just swap this guy and this guy. So now I've just redrawn this by swapping these two measurements up here. And now suppose I imagine that these two guys are off in one region of space, and these two guys are the possibilities for your choice of measurement in another. So Alice has to choose between M1 and M3. Bob has to choose between M2 and M4. So imagine that M1 and M3 can't be jointly measured. I mean, that's the fact that there's no edge here tells me they can't be jointly measured. M2 and M4 can't be jointly measured. But M1 and M4 and M1 and M2 can be jointly measured, and similarly with these pairs. And so this is just like the Bell scenario. Alice chooses one of two complementary measurements. She can't do them simultaneously. She has to commit to one. So does Bob. And they look at the correlations between the outcomes of their measurements. And if you tell me that the correlations are like this, I have to have agreement here, agreement here, agreement here, and disagreement here. This is precisely what's called the Popescu-Roerlich correlations. Okay, so the Popescu-Roerlich correlations are exactly one of these frustrated networks. And just as we saw before, the limit on how well you can do in a non-contextual model is 3/4. But now in this situation, you can say the reason the outcome of this measurement does not depend on which of these other two measurements it's been done in conjunction with is because of locality. If the outcome I got here depended on whether Bob chose M2 or M4, that would be a non-local influence, because this choice is being made outside the backward light cone of this measurement. So non-locality proofs are like contextuality proofs, but where the context independence is guaranteed by assumptions of locality. So I thought it would be useful for you to see that sort of connection. But fundamentally, you could say that sort of the deeper mystery is that when you have this scenario of measurements that you can't do simultaneously, like our simple example back here, this guy here. When you have this scenario, it now becomes possible to have these strange kinds of correlations. If it were always the case that the correlations arose by virtue of some set of outcomes, they would always satisfy these inequalities. The only reason it's possible to have disagreement on all these things is because you never measure all three of them at once, right? When you go to the lab, you have to commit to choosing some pair of them, and you'll always see anti-correlated outcomes when you measure that pair. But you never find any contradiction because, let's say you get the green and the red outcomes here. You can't go and measure M3 and ask, was it green or was it red? If you found one of those two results, then you would obviously sort of contradict either this link or this link. But the fact that the theory tells you can't measure it says that it's possible to have these kinds of correlations. So complementarity buys you the possibility of very strange correlations that you can't explain with one of these non-contextual models. Okay, so I'm trying to give you sort of a deep feeling for what contextuality is about using these simple examples. But let me now sort of start over again and tell you in kind of more detail why non-contextuality is a natural assumption and how it works. Okay, so remember what we said about hidden variable models. So your operational theory just says you have some preparation procedures, but a hidden variable model says you have a space of physical states labeled by lambda, and every preparation procedure gives you a distribution over that space. And a measurement is, again, just a set of conditional probabilities for the different outcomes given the different possible physical states. And you reproduce the probabilities in this way. And so far, nothing I've said here allows me to derive a contradiction. So I can find hidden variable models of quantum mechanics that reproduce the quantum predictions in this way. I haven't added enough assumptions to get any contradictions. It's only when I start saying, and I want nonlocality, and I want noncontextuality, it's only then that you can start having problems reproducing the quantum predictions using one of these models. So in this sort of language, what is the assumption of noncontextuality? So here's the idea, that an ontological model, so first of all, noncontextuality is a property of one of these hidden variable theories. So a hidden variable theory or an ontological model is non-contextual if whenever two experimental procedures are operationally equivalent, and I'll tell you what I mean by that in a moment, then they should be represented equivalently in the hidden variable model. That's the idea, that if I have two procedures in the lab and they're equivalent from the perspective of all statistics I might get about them, then I should represent them in the same way. Okay, so let's go into this operational equivalence notion carefully. So say I have a whole bunch of different preparation procedures I might do in the lab. They're all preparing the same kind of system, but they're different sorts of preparations. So in quantum mechanics, these might correspond to preparing different quantum states. And I have a whole battery of tests I can do on any one of these preparations. So then I'll put two preparations into the same equivalence class if I find that they have the same statistics for all measurements. So what I mean is if I take P1 and I put it in front of every one of these measurements and I write down the statistics I get for every one of those measurements, and then I take P4 and I do the same thing, and then I compare, and I find P1 and P4 give the same statistics for every single one of my measurements, then if you were to put P1 or P4 in a black box and pass the black box to me and say, try to figure out which one's inside the black box, so there's an aperture that spits systems up, I could put all of my measurements in front of it trying to figure out whether it's P1 or P4, and I would never succeed because they give exactly the same statistics. So in that sense, they're operationally indistinguishable. There are still differences between them. So for example, the things that you do in the lab to implement this procedure might be very different from the things you do to implement that procedure. So they're still different things. But from the perspective of the statistics of future measurements, they're totally indistinguishable. So in that case, I'll call them operationally equivalent. So I can sort all of my preparations into operational equivalence classes. Note that I don't have to assume quantum theory here. I'm trying to define for you a notion of non-contextuality that's applicable to any theory. So here I'm just saying you've got a theory, it makes predictions. We're only going to talk about the equivalence classes. Okay, so technically P is equivalent to P prime if for all measurements the distribution over its outcomes is the same for P as it is for P prime. So that's a difference of equivalence class, and what's left over, differences among preparation procedures, I'm going to call differences of context. Okay, so that's how you happen to have implemented that procedure. So for example, in quantum mechanics, the difference equivalence classes are always associated with different density operators. Two different density operators will always predict different statistics for some measurement. But there's many ways of getting at a particular density operator. So there are still differences of context. So here's an example. If I prepare an equal mixture of the 0 state and the 1 state, that gives me the completely mixed state on that two-dimensional workspace. But if I prepare an equal mixture of the plus state and the minus state, so this is 0 plus 1, this is 0 minus 1, I also get the complete mixed state. These are two very different procedures, right? So in one of them, I flip a coin and I prepare, Z spin up or Z spin down, depending on the coin flip, and then I forget the outcome. And the other one, it's X spin up or X spin down. There's very different things coming out of those boxes, you might think. But operationally speaking, those two things are totally indistinguishable. So this is a non-trivial example of a difference of context. Which pure state ensemble was used to build the complete mixed state? Here's another example of a difference of context. If I just prepare this maximally entangled state and then ignore the second system, throw it away, or I prepare this maximally entangled state and then throw away the second system, In both cases, the reduced density output is the mixed state. But again, the procedures are very different. But if I just look at the system A, and I do measurements on it, I can't tell the two things apart. Okay, so what is a preparation non-contextual model? So this is non-contextuality for preparations. It's defined in the following way, that if two preparations differ only by context, so they're in the same equivalence class, then they should be represented by the same distribution over the hidden variables. So the idea here is that the reason you can't find any measurements to distinguish these two guys is because the physical state that's coming out of these is sampled from precisely the same distribution. So if you have like a whole ensemble of uses of a given one of these guys and an ensemble of uses of this guy, they're going to be sampled from exactly the same distribution, so it's going to be exactly the same ensemble. Of course, the statistics of all measurements will be the same, if that's the case. So it's a very natural assumption of the operational indistinguishability of these two procedures is to say the probability distribution of hidden variables that they're associated with is the same. That's why you can't tell them apart. So this feature would be sufficient for explaining their indistinguishability. It's not necessary. The alternative is that these two procedures are corresponding to different distributions over the hidden variables. And then to explain the fact that there's no measurement that can tell them apart, I would have to appeal to the fact that all of these measurements are somehow a little bit fuzzy, that differences between these two distributions just can't be recognized by any of these measurements, that these measurements coarse grain in such a way that you never see the difference between these two guys. So that's a possible explanation of why you couldn't tell the difference between P1 and P4. But it's somehow less natural than the explanation that's given by a non-contextual model. So let me give you some examples of non-contextual and contextual models. Well, first, this is the definition. If the two preparations have all the same statistics for every measurement, then the distribution over lambda is the same. Okay, here's a couple of examples. So suppose you have preparation procedures associated with these 4 quantum states, 0, 1, plus, and minus. And we know that if I mix these two guys, I get the completely mixed state. If I mix these two guys, I get the completely mixed state. So one hidden variable model is the toy theory that we saw in the last lecture, which basically has 4 physical states, and this guy's a uniform distribution over the first 2, this guy's a uniform distribution over the last 2. These are distributions over 1 and 3 and 2 and 4. And as I said in the last lecture, I mean, it's very natural that these guys mix to exactly the same distribution as these guys mix to. So here, these 2 different ensembles of pure states are mixed to exactly the same thing. So the completely mixed state is only associated with a single distribution in this model, regardless of how it was built up in terms of pure states. So this kind of model is preparation non-contextual. It explains the indistinguishability of this ensemble and this ensemble by virtue of the fact that this mixture of distributions and this mixture of distributions are exactly the same. So you're sampling from the same distribution in both cases. On the other hand, there are other models, like this here is a model due to Koch and Spekkens from 1967, where they said the physical states of the system also is described by a sphere. So the block sphere tells you where the quantum states are. This is a different sphere. This is now a lambda, a physical state system, but it happens to be mapped to a sphere. And when you prepare the quantum state 0, you're sampling lambda from a distribution that's 0 in the southern hemisphere and it has a cosine profile in the northern hemisphere. And when you prepare the state 1, well, then you're sampling lambda from a distribution that's 0 in the northern hemisphere and this profile in the southern hemisphere. And similarly for the plus and the minus states. And it turns out what you can prove is that if measurements correspond to just asking what hemisphere you're in, so if I measure, say, X spin, it's just asking whether I'm in the X, or Z spin would be just, I'm in the northern or the southern hemisphere. Then you can actually reproduce all the predictions of quantum mechanics for pure measurements with this kind of model. But now you'll notice that in this model, the mixture of these two guys is this kind of distribution, and the mixture of these two guys is this kind of distribution. So the fact that I can't tell these this mixture from this mixture is explained in this model by the fact that the measurements aren't fine-grained enough to see the difference between these two different distributions. So the measurements, remember, we're always just asking, am I in this hemisphere or the opposite hemisphere? So if I measure spin along some axis, in this model it's just saying which hemisphere am I in relative to that axis. And what you can prove is that if I carve this sphere up into two hemispheres in any way at all, the measure over each hemisphere for this distribution is exactly equal to the measure for this distribution. So you know, relative to these partitionings of the sphere, these two distributions are totally indistinguishable. And that's why, operationally, you can't pull them apart. So these are very different strategies for explaining the operational indistinguishability of these two ensembles. And the idea of a preparation non-contextual model is that it should be explained this way, not this way. So is that clear? Any questions about that?
Would I be right in thinking that the top four spheres on the right are also indistinguishable from one another?
These four?
Yeah.
No, because if I did a measurement, say, am I in the northern hemisphere or the southern hemisphere? So I've sampled lambda for this distribution. Then the outcome of that measurement will be definitely northern hemisphere. Whereas if I've sampled lambda from this distribution, the outcome of that same measurement will be definitely southern hemisphere. So actually, I can tell this guy and this guy apart with probability 1 by doing the right measurement. It is true that this guy and this guy cannot be, you can't tell them apart by a single measurement, right? You have to do measurements over and over again and calculate some statistics. So these guys are distinguishable tomographically. You know, if I do enough measurements, I can tell them apart. The only things that are really indistinguishable, even tomographically, is the mixture of these and the mixture of those. Then you get the same statistics for all measurements. Other questions? No? Does that mean it's clear, or? Okay, I hope so. All right, let me tell you about measurement non-contextuality now. So it's exactly the same idea that you can sort all your measurement procedures into operational equivalence classes based on the statistics of their outcomes. So I take this measurement and I put each one of them in front of all the different preparation procedures, and I calculate statistics similarly with this guy. And if I find that the statistics are the same for all, then I say, right, they're in the same class, and the only differences between them are differences of context. And so, for example from quantum mechanics, if I have this measurement is a measurement of this basis, I'm in a three-dimensional Hilbert space, measure this basis, and then just coarse grain over whether you got the 2 or the 3 outcome. You could do another measurement, which is measuring a different basis, so psi 2 prime, psi 3 prime. It still has psi 1 in common. And now you coarse grain over this 2, 3 outcome again. So really you're just measuring whether you're psi 1 or in the subspace orthogonal to psi 1. But the measurement devices actually differ, because to measure this basis or to measure this basis are really quite different measurements. And quantum theory says it doesn't matter how you've done the measurement. You know, all that matters is the projectors that are associated with that guy. So, you know, if I just wrote down the set of projectors associated with this measurement, it's just projector onto psi 1, identity minus projector onto psi 1. Similarly for this guy. The only difference is how I've resolved this two-dimensional projector here into one-dimensional subspaces. Here it was 2 and 3, here it was 2 prime and 3 prime. But the statistics do not care about how you make this decomposition of this two-dimensional projector. Okay, so the assumption of measurement non-contextuality is that if you have two measurements that only differ in context, then they should be represented by exactly the same set of indicator functions. So this is the conditional probability of getting outcome 1 in the measurement in lambda. This is the probability of getting outcome 2. It's the same for both of them. The alternative, of course, is that these guys could be associated with different sets of response functions. But again, if that's your explanation, then you have to say, well, the reason you can't tell the difference between this measurement and this measurement is because none of these preparation procedures produce a distribution over the hidden variables that's narrow enough to actually detect the differences that we see in these indicator functions. So all of these preparations would somehow have to give you smeared out probability distributions that were incapable of seeing the difference between this and this. So it's possible to explain the operational indistinguishability of these guys, even though at the hidden variable level they're different. It's just a less elegant explanation than if at the hidden variable level they were represented by exactly the same guys. Okay, so those are the definitions. The natural assumption is what I'll call generalized non-contextuality. So it's basically assuming both kinds of non-contextuality. And the reason is that basically these two kinds of non-contextuality are equally natural. So if you think one's natural, you should think the other's natural. If you think one's unnatural, then you should think the other one's unnatural as well. If you ask, well, why should you believe this at all? Why is it plausible? I think there's sort of a deep principle here, which is, I like to call the methodological equivalence principle. So if a difference in your setup is not distinguished in the observable phenomenon, then it shouldn't be distinguished in the ontological picture either. And so an example of this, a very successful example of this, is Einstein's strong equivalence principle. He says, if there's no experiment you can do that can tell the difference between being, say, free falling in a gravitational field or moving inertially in free space away from any gravitational field, if there's no experiment you can do that can tell the difference between those two scenarios, then you'd better have a picture of reality that says it's the same physical scenario in both cases. And his picture of curved space-time achieves that. It says the curvature of space-time in that elevator is exactly the same in those two cases. The explanation of all your experiments is exactly the same. You don't have some sort of coincidence wherein although the situation, the physics is very different, nonetheless you have this sort of coincidence of experimental results. No, the physical scenarios are exactly the same. So I think that's the kind of principle that makes this non-contextuality assumption plausible. Okay, questions about that?
I think you haven't connected it back to the sort of frustrated version of Spekkens.
Not only do you think that, it's also true that.
Well, I'm saying that now, so I thought maybe it happened.
No, you're right, I haven't, but that's why there's more talk coming. Shall I move on then? Okay. Well, what is the connection to what I said in the beginning? So comparison of the traditional notion with the generalized notion. Are you awake? Okay. So what I said was that the most general way of representing a measurement in one of these hidden variable models is for every outcome of the measurement, you associate a conditional probability for getting that outcome given that the physical state was lambda, a set of response functions of sum to 1. But in the early part of my talk, where I sort of said, imagine these measurements and the physical state lambda determines exactly what the outcome of the measurement is going to be. There's no probabilities there. There's either a red or a green outcome for every measurement. That, in this picture, would correspond to response functions that were everywhere 0 or 1. So once you told me what the value of lambda was, there would no longer be any ambiguity in which outcome occurred. So that's the assumption I like to call it outcome determinism, that once you specify the physical state of the system, the outcome of the measurement is completely determined. So what it means is that this notion of non-contextuality that I've just defined in the last few slides, non-contextuality for measurements, is not quite the same as that traditional notion we saw at the beginning of the talk. The traditional notion is really my refined notion together with the assumption of outcome determinism. And therefore, if you had a no-go theorem for these kinds of notions, and that's what Cauchy and Specker proved back in 1967 for quantum theory, well, that's not necessarily a no-go theorem for this notion, because if you've got a contradiction from this assumption, you could always say, what fails is this guy, this assumption here of outcome determinism. So as long as I'm willing to say, oh yeah, the outcomes of measurements aren't determined by the hidden variables, then I can salvage this notion of non-contextuality I just defined. So this is to say that this generalized notion that I've just told you about and that I've tried to motivate by comparing it with Einstein's equivalence principle, it's not quite the same as the one that you'll read about in Cauchy and Specker's paper and in a lot of other papers and textbooks. It's a weaker notion. But fortunately, you can prove something nice, which is that this extra notion of non-contextuality that I told you about, preparation non-contextuality, together with some facts about quantum mechanics, like the fact that if I have orthogonal quantum states, there's a measurement that in a single shot can discriminate them, actually implies that you have to have outcome determinism for projective measurements. So you can essentially recover the traditional notion of non-contextuality using non-contextuality for measurements and for preparations, because non-contextuality for preparations implies this guy. And so that's nice because now all the old no-go theorems that people derive starting from this assumption can be rederived starting from non-contextuality for preparations and for measurements. Now, I don't think I'm going to go through the proof of this connection because, well, this is sort of a, I don't know, I think this is sort of a subtlety in the whole business. I don't think it's really that important for you to know how this works. If you're confused about the two different notions of non-contextuality, hopefully this gives you a bit of an idea of how they're connected. My view is that this general notion that I showed you in the second half of the talk is kind of much better motivated than the original notion. So it's nice that you can derive the original notion from this notion. But I'm not going to go through the proof of this. Okay. I want to focus on, in the rest of the talk, on this notion of preparation non-contextuality. When did we begin? I don't know how long
We started at about 10 past, so you've got just over 20 minutes.
Okay, perfect. Okay, so I want to talk more about preparation non-contextuality. And so I'm going to set it up like a game. So this is, I find that the best way to understand things like Bell's theorem and other quantum advantages is, invent a game between Alice and Bob and then show that the quantum team can do better than any classical team. I think that really highlights what's strange about quantum mechanics. So I'm going to tell you about a game that some co-authors and I invented to try to highlight what's weird about the fact that quantum mechanics fails to be preparation non-contextual. So here's the game. You imagine two players, Alice and Bob. Unlike Bell scenarios, where we always imagine that Alice and Bob are space-like separated, in this game they're time-like separated. So Alice is sending information to Bob. Okay? And the referee, or the verifier, Victor, sends Alice 2 bits of information that Victor chooses uniformly at random. So x0 is the first bit, x1 is the second bit. And he sends 1 bit of information to Bob, which I call y, and he asks for a bit of information back from Bob. And the idea is that Alice and Bob win if Bob's bit is x sub y. So effectively, Victor is telling Bob, tell me what the first bit I sent to Alice was, or he's saying, tell me what the second bit I sent to Alice was. And Bob just needs to report what the value of that bit. And so far, there's no problem. If Alice just sends both bits over to Bob, then he can always report whichever bit Victor asks for. Now here's the catch. Victor's going to demand that whatever Alice sends to Bob, it's not allowed to contain any information about the parity of those 2 bits. So the parity is the sum mod 2 of x0 and x1. So imagine that Victor is going to occasionally check and punish them if there's any information about the parity. So Alice is concerned not to send anything that contains information about the parity. Now it becomes non-trivial. How well can they do in this task? So I'll first consider how well they can do in a classical world. So first of all, if you look at any function that depends non-trivially on both x0 and x1, it reveals some information about the parity. So if Bob gets some information about the values of x0 and x1, then he can infer something about the parity. He's not totally in the dark about the parity. So that means that Alice is not allowed to send him any function, the value of any function that's non-trivial for both of them. So she has to basically just send him some function of x0 alone or some function of x1 alone. And so, an optimal protocol would just be for her to always send him x0. And let's say, that this is the protocol they agree on, so Bob knows he's just going to get x0. So in that case, if it so happens that Victor asks him for x0, and that happens half the time, well then they win with probability 1. But half the time, of course, Victor asks for the other bit. He asks for x1. and Bob has no information about x1, so he just has to guess. And he has probability half of guessing correctly. So the overall probability of success is 3/4 in a classical world. Good. Okay, so now what about other worlds? Here's an imaginary world. It's not quantum, it's not classical. I've basically engineered it to do, it's a world where you can do this game really well. So here's the idea. There are systems in this world that have 4 states. And you can prepare those systems in exactly one of the 4 states, so you can control which one of them is prepared in. But the only measurements you can do are ones that distinguish the first 2 and the second 2, or the 1 and 3 from 2 and 4. And you can't do this third measurement here. So it's not like the toy theory we saw in the last lecture, because in the toy theory you can do that extra measurement. If this is the world, then Alice can just encode her 2 bits into these 4 states. So just think of these in binary, 0, 0, 0, 1, 1, 0, 1, 1. Whatever the values of the 2 bits are, she just prepares the appropriate state. Sends it over to Bob. Bob gets this y from Victor. So he's either going to try to distinguish, if he wants to know the first bit, he's trying to distinguish 1, 2, and 3, 4. Because the 1 and 2 are the 0, 0, and 0, 1 cases. And the first bit is 0. 3 and 4 are the 1, 0, and 1, 1 cases. So the first bit is 1. So if he wants the first bit, he does this measurement. If he wants the second bit, he does this measurement. So he can always find out whichever bit he wants. And then the reason he gets no information about the parity is that he can't do this measurement. And the assumption is that there are no other measurements, and so no measurement can reveal anything about the parity of x naught and x1. So this is a world in which you can, Alice and Bob can succeed with probability 1 in this game. But there's something weird about this world, which is that if you look at certain mixtures of these preparations, like the mixture of 1 and 4 and the mixture of 2 and 3, these guys are totally indistinguishable from the perspective of all measurements. No measurement you do on these 2 guys will ever have any different statistics. And yet they're totally different at the hidden variable level. They actually correspond to mutually exclusive physical states. Every physical state that's consistent with this guy is inconsistent with this guy. That's preparation contextuality. Things that are different at the hidden variable level, but nonetheless indistinguishable at the operational level. The idea is that's kind of unnatural for a world to be like that, for these 2 things to be so different and yet no measurement to be able to tell them apart. So here's an example of a world where we can do well at this task, but it's at the price of being preparation contextual. Here's another example, the quantum world. You can also do well at this task in the quantum world. And it's also the case that quantum mechanics is not preparation on contextual. It has contextuality. So here's the idea. Alice encodes her 2 bits in 1 of 4 quantum states, located at these 4 points on the block sphere. And then if Bob wants to get the first bit out, he does this measurement. And this measurement is such that if the state was one of these 2 guys, with 85% probability gets this outcome, 15% probability gets this outcome. So he gets a pretty good estimate of the first bit. If he wants the second bit, he does this measurement. And now, again, he has an 85% probability of guessing the second bit correctly. So overall, his probability of guessing correctly is 85%. And furthermore, if I look at the mixture of 0, 0, and 1, 1, that's the parity 0 case, it's the completely mixed state. And the mixture of 0, 1, and 1, 0, also the completely mixed state. So there's no measurement Bob can do to tell the one mixture from the other mixture. So this scheme is also parity oblivious. No measurement Bob can do gets any information about parity. So it satisfies that part of the definition. But this probability is greater than 3/4, so it does better than the classical one. Now, so this leads you to think, well, maybe to do better than 3/4, you need contextuality. Maybe 3/4 is actually the upper bound that any non-contextual theory can at best do 3/4 of this task. And that's right. So I'm going to prove this theorem to you. For all theories that allow for hidden variable models that are preparation non-contextual, your probability of success at this task I've defined is upper bounded by 3/4. And so this is, again, another example of these non-contextuality inequalities. I can calculate this probability just from measurement statistics, right? It's simple, it's an operationally defined quantity. How often do you win this game? And if I violate this inequality, then it tells me that no hidden variable model for that experiment exists, which has this nice feature of being non-contextual. It's going to have to be one of the weird, unnatural models where things that are indistinguishable at the operational level are nonetheless different at the hidden variable level. Okay, so what's the proof? Well, here's our experiment. If I have any protocol for doing this, it's going to have to define 4 preparation procedures. One for every pair of values that these 2 bits contain. So there's these. Here are the 4 preparation procedures. Bob is going to have to choose 2 measurement procedures for the 2 values that Victor sends him. And every one of those measurements has 2 possible outcomes, 0 or 1. And he's just going to report the outcome of that measurement as his bit. So now let me define 2 effective preparation procedures. So the first one, which is like a parity 0 preparation, is just an equal mixture of the preparations that correspond to these bits having parity 0. And the second one is an equal mixture of the preparations when these bits have parity 1. So these are preparations that just coarse grain everything except the parity. And the point is that the constraint of parity obliviousness is that no matter what measurement Bob does, so for all measurements Bob might do, his statistics, the probability of the different outcomes, has to be the same for the parity 0 preparation as it is for the parity 1 preparation. If there was some measurement that gave different statistics, then he would have acquired a little bit of information about what the parity of those 2 bits are. So this is the parity oblivious condition. And now the assumption of preparation non-contextuality allows us to make inferences about the distribution over the hidden variables. It says, look, this preparation and this preparation are operationally indistinguishable. No measurement gives different statistics. So they have to be represented by exactly the same distribution over the hidden variables. That's the assumption of non-contextuality. And then it's just enough to do a Bayesian inversion. So these 2 preparations are equally likely. So I can just Bayesian invert these probabilities. And I can interpret this formula as saying, if the physical state of the system that's passed from Alice to Bob is lambda, is known to be lambda, then it's equally likely that the parity was 0 as it is that the parity was 1. So what this says is that even if you could learn somehow the value of lambda, even if Bob had a super powerful measurement that found out exactly what lambda was, and typically he doesn't, but suppose even that he did, it still wouldn't tell him anything about the parity, because the probability for parity 0 and the probability for parity 1 have to both be a half. And so he learns nothing about the parity, even if he has the state of the hidden variables. But that's exactly what was the constraint on our classical model. You know, lambda here is just a classical variable that gets transmitted from Alice to Bob, and it has no information about the parity. So we already derived how well you could do with that kind of classical explanation. The answer was you could at best do 3/4. So, you know, the point is that the hidden variable is just like a classical message that Alice sends to Bob. It has no information about the parity. And so any preparation non-contextual model of this experiment, or if there is a preparation non-contextual model of this experiment, then you will succeed at most 3/4 of the time. All right, so this is, you know, what's the use of this parity oblivious multiplexing? You know, where Alice can send, so Bob basically gets to choose whether he wants to know about bit 0 or bit 1, and he can sort of get more information about each individual bit than you would expect classically. So that's the sense in which it's multiplexing. Alice is sort of sending him both information about 0 and the first bit, and information about the second bit, and Bob just has to choose which one he's going to get. It's kind of a weird task, and you might say, well, what's it useful for? I don't know. As far as I know, it's not useful for anything. But it's just a sort of proof of principle that there are information processing tasks that are powered by contextuality, this strange feature of quantum mechanics. And it's also nice that, you know, with these kinds of inequalities, you can now go to the lab and say, we'll do this experiment, we'll verify that no measurement can tell, let's see, how do I have it? Yeah. Suppose you implement it in the lab this way. You really try to prepare these 4 quantum states, and you try to verify that indeed there's no measurement that can tell this mixture and this mixture apart. So you will get evidence for this parity oblivious property. then if you find that you violate this inequality, you have good reason to think that the hidden variable model, any hidden variable model that could describe your experiment has to have this unnatural contextuality in it, even if quantum mechanics is wrong. So you haven't assumed quantum mechanics here. We've derived these inequalities without assuming quantum mechanics. So even if quantum mechanics is found to be wrong tomorrow, this experiment would still show that whatever theory is going to replace it, it's a theory which does not admit of a hidden variable model that's non-contextual. So just like Bell's theorem, Bell expresses a notion of locality that is theory independent, doesn't rely on quantum mechanics at all. You violate a Bell inequality, you conclude whatever theory is true of the world, whether it be quantum mechanics or something else, there's no local hidden variable model that can underlie it. So the same thing is true here. There's no non-contextual hidden variable model that can underlie the statistics of an experiment that violate this kind of inequality. Okay, and I should mention that a group of Jeff Pride in Australia has done this experiment and violated this non-contextuality inequality. Okay, so I should wrap up, I think. I'll say a couple things about the connection with non-locality in a moment. But if you ask, well, what's mysterious about the contextuality of quantum theory? It's the following tension, I would say, that on the one hand, you find these violations of non-contextuality inequalities, which suggests that the distributions over hidden variables do depend on things like the value of the parity. So what it suggests is, the only way you can hope to explain this stuff with a hidden variable model is that, the parity 0 and the parity 1 preparations really do correspond to different distributions. So the information about the parity is there in the physical state that gets transmitted to Bob. That's why he can do so well. It's just the fact that his measurements can't get at it. That's the surprising thing, is measurements can't get at it, but the parity information's got to be there in the hidden variables on his side to explain how well he can extract both the information about bit 1 and the information about bit 2. If the information wasn't there, how could he possibly get it? Right? So you sort of imagine on the one hand that there must be some information about the parity that makes it to Bob. And yet on the other hand, he can't extract any of that information. So Alice can't communicate information about the parity to Bob. So that's bizarre, that the information's there and yet you can't get at it. It's unnatural. Much like in Bell's theorem, it seems like any hidden variable explanation needs to have superluminal influences to explain the Bell inequality violations. That's the way, that's one way of thinking about Bell's theorem, that there's got to be some influence from the choice of setting over here to the outcome that Bob gets. And yet, there's no way for us to use that influence to actually send signals fast in the speed of light. That's very odd that those two facts should be true. And so I think it's completely analogous for the case of contextuality. So let me end by saying one more thing about Bell's theorem and non-locality, connecting it up to what I've told you today. So say you take a standard Bell setup. So here you prepare error systems. Oh, actually, maybe I should, before I move on to that, I should ask, are there any questions about the stuff that came before? Yes?
I don't really understand what good you get from a contextual hidden variable. If I understand what contextuality is, because you're now saying that what was once before it was a kind of physical property of something. Now it doesn't even just depend on that thing, it depends on the measuring part. I mean, it seems like this is what Bohr was talking about when he said the irreducible, properties are sort of irreducible rise out of some kind of irreducible interaction between the measurement parameters in the system. I don't know if I've understood this properly, but it seems like a contextual hidden variable, if it depends on the way you do your measurements, then it isn't even really a property of your system anyway.
Well, okay, let me think. There's sort of two things, what are the kinds of things that can depend on context in this approach? Like, just a general question, when we say something has context dependence, what is that thing we're talking about? And in this approach, the things that depend on preparation context are the distribution over the hidden variables. Okay, so for example here, the shape of the distribution could depend on the preparation context, features of the preparation procedure. So for example, here I could be preparing, an equal mixture of z spin up and z spin down. Here I'd be preparing an equal mixture of x spin up and x spin down. That's a difference. And it could be that the shape of the distribution depends on that difference. So that's not a dependence of that distribution on what's going to happen later with the measurement. It's just a dependence on some feature of the preparation that is irrelevant to the statistics of those future measurements. So if I was just trying to predict the outcomes of one of these guys, I wouldn't have to tell you whether I'm P1 or P4. It's irrelevant, right? I could just tell you what class I found it. But if I want to tell you what the distribution over the hidden variables looks like, well, then I need to know whether I'm doing this or this. So it's not quite a Borean dependence on something else. It's a dependence in the hidden variable model on something which, in the operational approach, we don't need to talk about. We don't really need to talk about whether I prepared a mixture of z up and z down or x up and x down. It's irrelevant to the statistics that are coming later. I could just tell you, look, I prepared something that's identity over 2. Now go off and make your predictions. And you'll say, great, that's all I needed, thanks. I can now make all the predictions that I would have been able to make if you just told me that it was a mixture of z up and z down. But if you're in the business of building a hidden variable model, and I said, oh yeah, there's a preparation procedure that's been done, it's associated with the quantum state identity over 2, you would say to me, I'm sorry, you haven't given me enough information. I want to write down the distribution over the hidden variables, and you need to tell me, is it identity over 2 that comes from a mixture of z-spin eigenstates, or is it identity over 2 that comes from a mixture of x-spin eigenstates? That's going to be relevant for the distribution I write down. Because if I don't have that difference, then I can only associate a single distribution, and then all my predictions are non-contextual. So I don't know if that helps answer your question.
You're still saying there's a physical state. It's just the contextuality is in how you assign new probabilities.
That's right. It's a dependence of the distribution over the states on the context. Not in some ways not a dependence of the state itself, but the distribution of the state. And then conversely, if we're talking about the measurements, it's a dependence of the conditional probabilities that relate the outcome to the physical state. That's the thing which depends on the context now. So you might have again thought, usually if I just tell you, here is the set of projectors associated with your measurement. Now go off and predict what the outcomes, the statistics of outcomes are going to be for various different preparations. You're like, great, that's perfect for me, I can do that. But if you're trying to build a hidden variable model and I only tell you the projectors, you might say, that's not enough. I need to know, is this rank 2 projector a coarse graining of these 2 rank 1 projectors or a coarse graining of these other 2 rank 1 projectors? Because that's going to be relevant to what kinds of response functions I write down. Other questions? Yes?
Define 2 preparation procedures to be in these equivalence classes. If the ensemble measurements couldn't distinguish between the 2, so you build up some probability distribution. And you said that this is a set of all possible measurements, or
yes?
Okay. It seems that in that game that you were talking about, you could measure in a diagonal basis, and the ensemble measurements would then be able to distinguish between the preparations.
Do you mean the particular example I gave of the 2 ways of decomposing identity over 2?
No, I'm talking right at the end when you said that if you want to do this game with the x1, x2 bits.
Yep.
And then bottom edge in the.
Yep, I can do that.
Yeah.
Here we go.
Yes, that's right. It seems you're saying bottom edges in either the red line or the horizontal or vertical.
That's right.
And that's his best chance of, with a one-shot measurement, distinguishing between giving the right bit.
That's right. So his task is always either to guess the first bit or to guess the second bit. It depends on what the victor has asked him to do. So this is why he just needs to do a 2-outcome measurement. And he wants to cater that measurement to what Victor is asking him for. So if he's interested in figuring out the first bit, he just wants to distinguish this pair from this pair. And so so this measurement does a good job of that. It distinguishes this pair from this pair. If he wants to distinguish this pair from this pair, that's finding out whether the second bit is 0 or 1. This is his optimal measurement. if he did the measurement here, for example, he could get some information about the first pair and some information about the second pair simultaneously. But the problem is that he would be doing worse. Like he's already gotten the message from Victor. You know, Victor's told him, I want bit 1. So why should he go and do a measurement that's not optimal for reporting what bit 1 is? It's better to do this measurement. And then
I was just sort of complaining that there is measurement you can do that if you allow Alice and Bob to repeat the procedure many times, then he could tell with his measuring apparatus which of the 4 states Alice sent.
There's no measurement he can do to distinguish 4 non-orthogonal states for a single two-dimensional space.
Okay.
Not in one shot. And if you say, well, what about tomographically? What can he do? But the important thing is that he can even, not even tomographically, can he distinguish the 0, 0, 1, 1 pair from the 0, 1, 1, 0 pair. Like if somebody says, look, I don't care exactly which of the 4 it is, just tell me whether it is in the set 0, 0, and 1, 1, or the set 0, 1, 1, 0. The problem is that when I mix these two guys, they give me the completely mixed state. I mix these two guys, they give me the completely mixed state. All measurements give exactly the same statistics for those two mixtures. So there's nothing he can do to tell those two guys apart. Somehow we've lost.
Yeah, so I got to keep some. Hold down the other one.
So Alice isn't actually sending a pure state.
Yeah. Well, she is sending a pure state. She's sending one of these 4 pure states. But when you ask, what's the discrimination problem Bob has to do to learn about the parity? It's a mixed state discrimination problem. He's trying to distinguish one set of pure states from another set of pure states. And so it's equivalent to asking, can he distinguish the mixture of the first set from the mixture of the second set? And the problem is that the mixture of the first set is exactly equal to the mixture of the second set. Yeah. And so he can't tell those apart. So maybe I should say that, in the last lecture I said, look, this fact that we're familiar with from quantum theory, that a given mixed state can be decomposed into a convex combination of pure states in many different ways. Like, it can be decomposed into Z-spin eigenstates or X-spin eigenstates. In that toy theory I showed you, that was sort of very natural. It just said, oh, look, the pure states are these states of non-maximal knowledge, and so there's just different ways of carving up a phase space into states of non-maximal knowledge, sort of this way and this way. And those, the reason we can't tell those two mixtures apart is because of the same distribution. That was preparation non-contextuality. That was an explanation of the ambiguity of quantum mixtures that was totally preparation non-contextual, and it was very natural. But what I'm telling you now is that, unfortunately, if we look at the full quantum theory, rather than just Gaussian quantum mechanics or stabilizer quantum mechanics, we can't have that nice feature. We can't explain the ambiguity of mixtures in that way. We can develop these much more subtle kinds of experiments that show us that a given mixed state has to be associated with many distributions over the hidden variable, not a single one. And so this is sort of what I was saying to you about how I was trying to convince you that there's a lot of features of quantum mechanics that at first look weird, like this ambiguity of how you decompose a mixed state into pure states, that don't look weird if you take this view that quantum states are states of knowledge. But now sort of the weirdness is back, because I'm saying it's not just the existence of the ambiguity of mixtures, it's this very particular choice of the statistics that you get. The fact that I can set up a system where Alice can send Bob information about bit 0 and bit 1 with high probability, even though Bob gets almost no information about the parity. That's a much more refined kind of feature, and it's what these hidden variable models can't achieve. So anyways, I hope I've convinced you that the sort of the weirdness of quantum mechanics is a lot more subtle than you might have thought at first. At least I've convinced you that it's all kind of subtle, because this is subtle. All right, well, we're kind of out of time because I started at 10 past. So I could just end here. Or I could take a few minutes, 5 minutes to...
I don't know. You might as well finish, and we had a few questions, so I guess we have less questions at the end.
Okay. All right, so what's the connection with proofs of non-locality? So if you have a proof of non-locality, what you've got is a preparation procedure that spits out two systems, and then you've got a measurement procedure on both wings, and these are done at space-like separation. And you can set things up so that, so if you prepare this entangled state, and you do this measurement on the block sphere for one of your measurements, and this measurement on the block sphere for the other measurement, similarly here and here, then you can find that the probabilities for correlations for any pair of these measurements have this profile. So for S and S, it's 85% correlation, S and T correlation, T and S correlation, T and T almost perfect anti-correlation. So this is the probability that violates what's called the CH-SH inequality. Now, okay, let's think about this from the perspective of everything we've been talking about. I said in the lecture on psi epistemic invariable models that we should think of the phenomena wherein I do a measurement over here and collapse the quantum state over here as just pure Bayesian updating, right? So I said, suppose you do the 0-1 measurement on this state. Well, you collapse your description of the faraway state from the completely mixed state to either the 0 state or the 1 state, right? So if I get the 0 outcome on A, I collapse B to 0. If I get the 1 outcome on A, I collapse B to 1. So I collapse to one of these two guys. This is sort of picking out a term in a convex decomposition of this guy, right? So this guy decomposes a half 0 plus a half 1, and so I'm just sort of resolving my knowledge to this guy or this guy. Similarly with the plus-minus basis, I'm resolving the identity into either plus or minus when I do collapse. So you might have thought in a hidden variable model, all that's going on here is I start out knowing something about lambda b, the physical state of this guy, that's new lambda b. Lambda a and lambda b are perfectly correlated. And when I learn something new about A, I just update my knowledge of the distance system B to from nu to mu naught or mu 1, where these guys are a couple of distributions that sum to nu. And if I do some different measurement on A, I'm just updating my knowledge from nu to either mu plus or mu minus, which is a different way of resolving my knowledge. So the example we saw from the previous lecture was, if I measure position over here, I update my knowledge about the distance guy so that I know what the position is. Or if I measure momentum here, I update my knowledge of the distance guy to know what its momentum was. I can't know both, but I can resolve my information in these two different ways. So you might have thought, well, yeah, that's exactly what should be going on in this experiment. That all that's happening is not a non-local influence. It's just I'm updating my information in these different ways. So what this says is that the locality assumption can actually justify preparation non-contextuality in this context. So it's basically saying that these two ways of decomposing the completely mixed state, this one and this one, should be represented in the hidden variable model as two decompositions of the very same distribution, right? That's an instance of preparation non-contextuality. The mixture of 0 and 1 on this guy should be the same as the mixture of 0 and plus. They should both be represented by nu. And what I'm saying is that you can justify that by locality. If the measurement here, the choice of measurement here, only specifies how I update my knowledge and not how the variable is distributed overall, that's because of locality. If nu, if I could have nu here and nu prime here, that would say that the distribution over lambda b depends on what you chose to measure here. That would have to require some sort of non-local influence from my choice of measurement here to the actual values of the hidden variables on the other side. So if I want this collapse to be just pure Bayesian updating, then it better be that nu is the same for these two guys. And that's just another way of saying that locality, in this case, implies preparation non-contextuality. But now here's the problem. If the measurements you do here are in this basis and this basis, so that you collapse the distance system to one of these eigenstates or one of those eigenstates, and then the measurements you do here are this basis and this basis, well, that's exactly the structure we saw from my proof of preparation contextuality. This is exactly the scenario wherein I can't imagine that the mixture of this and this is the same distribution over the hidden variables for the mixture of this and this, and still do justice to the quantum correlations. So what it says is that if you try to think of this scenario as just Bayesian updating about the hidden variables, you can't explain the statistics you get in the experiments. It doesn't work. So I showed you this nice example last time of how, with the EPR scenario and just position or momentum, it really works out nicely that, it just looks like Bayesian updating of a distant system. Nothing funny going on. But when you change the measurements to be these different bases on the block sphere, that sort of picture doesn't fly. And so that's the sense, again, in which the stuff in column 2, like Bell's theorem, rule out these simple kind of hidden variable model explanations of what's going on in quantum mechanics. There's something weirder here. But as I say, it's these more intricate features of quantum theory. So the EPR paper by itself didn't prove that there was any kind of spooky action at distance in quantum mechanics. I mean, that's sort of the tragedy of it. Einstein was saying, it's only if you believe the crazy things that Heisenberg and Bohr believe that you're going to be forced to think spooky action. If you believe what Einstein believed, that the quantum state is just a distribution, it's just Bayesian updating, it's no problem. So from 1927 or 1935 onwards, anybody who sort of bought Einstein's argument would say, yeah, we can have locality as long as we treat the quantum state as just describing our knowledge. But then 1964, Bell shows, sorry, even if you treat the quantum state as just describing knowledge, you still can't have locality. But you have to look at these more refined kinds of experiments. Position and momentum alone won't show you that. So I think I just wanted to end by saying, the analogy between non-contextuality and non-locality is that you have, again, a tension. You have Bell inequality violations, which suggest that there should be some superluminal causation, but you can't use it to signal. And that's what's very weird about quantum correlations. And so I think with that,